Welcome to part D of lecture 3, and here we're going to be talking about the Arrhenius equation and looking at how it applies to the idea of rates. So Svante Arrhenius was looking at these rate laws and realized that something must be controlling this value of k, so the rate constant. The fact that it stays constant under a given set of conditions, and then if you change those conditions, the value of k changes. And so he figured that there must be some inherent factors to a reaction that remain the same given certain conditions, and then if you change those conditions, you're going to change these inherent factors as well. So he was looking at things like energy of the collisions, the collision frequency, collision geometry, and something called the activation energy. And so he put together something that is called the Arrhenius equation. Now, the Arrhenius equation has several different forms. This is one of the more complex forms that we don't use very much. And the reason we don't use it very much is because of this guy right here, the frequency factor, which is really a value to make this equation work. But we have ways of working this a value out of the equation to make the Arrhenius equation a little bit more useful and a little bit easier to use than in this form. But this is something that Arrhenius was really trying to do, was to find what kind of things contribute to this value of k. And so we see that we've got the frequency factor there. So that had to do with the collisions, the collision frequency. And then we've got this exponential term over here, e to the negative ea over rt. And this whole term here really represents this fraction of molecules that have a minimum amount of energy required to react. So let's take a look at that. So temperature and collisions. We've talked about temperature's effect on reaction rate. We said that as temperature increases, that molecules begin to move faster and that they collide more often and they collide harder. Now, why does an increase in temperature make things move faster? Well, if we think about what temperature is a measure of kinetic energy. Kinetic energy, of course, from physics has the equation of 1/2 mv squared, mass times velocity squared. Well, if I add energy, thermal energy, to a system to increase its temperature, I only have two variables to change. I can either change its mass or I can change its velocity. Well, adding energy isn't going to change its mass. So in order to change that kinetic energy, I must be changing the velocity. So only that's the only variable that is possible to change. So as a result, raising the temperature increases the amount of kinetic energy present in that system, and that means that the molecules within that system must be moving faster. So they collide more often and they collide with more energy. Now, one of the things that we see is this idea of thermal energy distribution, and this is really kind of a nice graph. So what we have here is we have the fraction of molecules with a certain amount of energy, and then energy here itself. And what we have is something called a Boltzmann's distribution of energies. And so at a cold temperature, we have T1. Let me just go ahead and go to a laser pointer here. So we have T1 here. And we can see that we have an exponential decay. So even though you have a sample of molecules at a single temperature, there is still a distribution of energy within that within that sample of molecules. This is the reason why, let's say that you're home and you spill a little bit of water on your table and you feel like being a slob and you don't feel like cleaning it up because it's not very much water, it's not going to affect anything. If you go away for a few days and come back, you'll probably find that little spot of water that you spilled is gone. Now, why is that? What happened to it? Well, I'm sure you know, as you think about it, you go, well, it evaporated. Okay, so we had water turn from a liquid to a gas, but the boiling point of water is 100 degrees Celsius. That's where liquid water turns into a gas. Pretty sure your apartment did not reach 100 degrees Celsius any time during your absence. So how did that water turn into a gas at a temperature much lower than the boiling point? Well, the reason is this graph right here. Notice that even at cold temperatures here, a sample of material some of it is still going to have enough kinetic energy to get up and over this idea of activation energy, the minimum amount of energy needed to make something happen, whether it be a reaction or a phase change. So there is a fraction of water molecules within a drop of water at room temperature. There's a fraction of molecules in there that have enough energy to go from the liquid state to the gaseous state, and they will do so. And so those molecules will leave. Now, once those molecules leave, all of these energies must redistribute. And so they'll absorb more energy from the outside, and it will redistribute here. And then what happens is you have another set of molecules that now have enough energy to evaporate, and they will evaporate into a gas. And then the remaining molecules will again redistribute their energies so that they match this physical requirement of this distribution. And so that continues to go until all of the molecules have eventually evaporated. Now, as we raise the temperature, notice that the line gets more spread out, but the area underneath, which represents the number of molecules with enough energy to get up and over that energy barrier, that activation energy, it increases. So if we have more molecules that can get over that activation energy, the faster that reaction will happen. And this is why if your apartment were really hot at 40 degrees during a hot summer day, that little puddle of water or drop of water is going to evaporate faster because more molecules at any given time have enough energy to get over that phase barrier from liquid to gas. So reaction rate goes up, bottom line. So let's look at this idea of activation energy. It was a term I threw in there and we hadn't really talked about it yet. So activation energy is the minimum amount of energy needed to react. When two molecules collide, or as we were just talking about, have a phase change, there's a certain amount of energy needed in order to either to break bonds, form bonds, or to escape intermolecular forces in a phase change. So activation energy in an equation is indicated by capital E with a little a after it. The big E is generally considered to be energy, and the little a down there just tells us that it's activation. Sometimes it's also called an Arrhenius energy, so the little a works for Arrhenius as well. So how does activation energy affect reaction rate? Well, it depends on what the energy barrier is in order for a reaction to go from reactants to products. If there's a low energy barrier, it will result in a fast rate because lots of molecules will have enough energy to go from reactants to products, and you'll have a very fast rate. If you have a very high energy barrier, then not very many molecules will have the energy at a given time to go from reactants to products. So you have a slow rate. So if you had that drop of water on your table, if it were 80 degrees Celsius in your room, a lot of the molecules would have enough energy to turn into a gas, and it would evaporate much faster than if you left the window open in the winter and it was 5 degrees in your room. Then it would have a very slow rate of evaporation because very few molecules would have enough energy to turn into gas. They still would, but it would take a longer period of time. And ways we show this idea of an energy barrier and what's the energy of your reactants and products is something that's called a reaction coordinate diagram, or an RC diagram. And there's one we see there. So this is something that's called a semi-quantitative graph. Semi-quantitative because the y-axis energy is quantitative. We'll have actual values of energy on there for energy of reactants, energy of products, energy of the transition state. But then the x-axis is just something vague, reaction progress from start to finish, and that's it. It's not time, it's just where are you in the process of the reaction. And so it's going to vary for different molecules at different times. So there's nothing quantitative about the reaction progress other than start and finish. So that's why this would be called a semi-quantitative graph. That's not real important to know, but if you ever hear that term, that's what it is. So some things that we get from the reaction coordinate diagram. one of the more important things that we get is it shows that highest energy point during the reaction. And this is generally where bonds are physically being broken, being formed, where you may have a rotation of some species taking place. It's a very high energy, very unstable point in the reaction. So we call this point a transition state, and we can see it right there on our graph. So this is our transition state right there. Okay, the species that exists at the transition state is something that is called an activated complex. So in this reaction here, we see that we have carbon bonded to nitrogen here, bonded to another carbon. So we have a triple bond, what's called a cyano group there, like this, and the reaction is going to turn the triple bonded NC group around 180 degrees. So the highest energy here is where you have a partial bond between the triple bond here and the carbon there, and it's a very odd type of bond there. It's not strong at all. It's very unstable, so it's very high energy, and so that's why it's that highest energy state. We call that the transition state. It's the transition point from reactant to product. Now, the energy it takes to get from the reactants up to the transition state is what we call the activation energy. So it has lots of different meanings or different representations. So this energy here is what we call our activation energy, and it's something that we can measure directly off of the reaction coordinate diagram. Now, if we go back to the Arrhenius equation that we had, I mentioned that it's not a particularly useful form because of that frequency factor, which is not particularly easy to find. It's not particularly easy to look up. There are some reactions where you can find it, but if you have a new reaction, it can be difficult. So that makes that equation a little bit difficult to use. But we can take that equation, we can rearrange it into a linear form, and that allows us to solve for the activation energy of a reaction, which lots of times we want to know because there are some ways of manipulating a reaction to lower the activation energy to make that reaction go faster. And so if you know what the activation energy is, you know if you need to do anything to it in order to help your reaction out. So if we go back to our original Arrhenius equation from the first slide, and we take the natural log of both sides, it removes that exponential. It turns the k term into natural log of k. This used to be e to the negative ea over rt. The log gets rid of that e. We have negative ea over r. We separated out the 1 over t to create an x variable, and then the a that was multiplied there. When we took the natural log, we can say plus natural log of a right there. We're allowed to do that. So that gives us a y equals mx plus b. So what you can do is, if you have a way of measuring the equilibrium or the rate constant and adjusting the temperature, you can plot 1 over t versus the natural log of k for several different temperatures of the same reaction and your different rate constants. And from there, you can find the value of your activation energy, and your y-intercept will give you the natural log of a, and you can actually find the value of that frequency factor as well, which you may or may not want to know, but it's there. Something else we can do with that particular equation is manipulate a little bit with two temperatures, and we get something that we use a lot more often in this class, and that's something called the two-temperature form of the Arrhenius equation. And the two-temperature form, because of the manipulation, it actually removes the frequency factor, that A value. And we eliminate it mathematically from the equation by using just two temperatures, and it gives us this equation here. So we have the natural log of K2 over K1 is equal to negative EA over R times 1 over T2 minus 1 over T1. Okay, so R, you may recognize from previous chemistry classes, that is your gas constant. However, it's not going to be in pressure volume units. It's going to be in energy units. So frequently it's giving as 8.314 joules per Kelvin mole. Okay, so that's our value of R. Your T's here, your value of R kind of dictates all the units that you want to be putting into this equation here. Notice that your R value has temperatures in Kelvin as a unit, so you've got to make sure that you use Kelvin. For T2 and T1, activation energy is very frequently given in kilojoules per mole, but notice that in your R value you've got joules per mole. Probably one of the most common mistakes is forgetting to turn your activation energy into joules, or you can also turn your R value into kilojoules per Kelvin mole. Either of those is perfectly acceptable. Pick one way to do it and always do it that way. It'll always work. You just have to remember to do one of those. And so this is generally needs to be converted into joules. That's the way I always do it. But I've seen people who convert R into kilojoules per Kelvin mole. It's exactly the same mathematically. Now, as far as the Ks, the only thing you have to make sure with the Ks is that the time unit is the same. When I say the same as each other, because notice that you've got K2 over K1, so as long as their units are the same, their units will cancel. When you take the natural log of a value, it has to be unitless. And so as long as their time units are the same, then all their units will cancel, and you'll get a unitless value there, which is exactly what you should have. Okay, so you can see some different forms of this equation depending on what they do with this minus sign or the minus sign out here. If this turns into a plus, then you get 1 over T1 minus 1 over T2. Lots of different ways to manipulate this particular equation and remain the same. This is the one I like to use. The reason I like to is because there's a lot less confusion. The log term is K2 over K1. The temperature terms are T2 minus T1. When I was sitting in a chair in college, when I was your age, I used to confuse these two all the time because our book had them flipped around and got rid of that minus sign there. And sometimes I'd accidentally flip this around or flip this around and get it incorrect. And so I like keeping things consistent. K2 over K1, T2 minus T1. I find that an easier way to go. So here's one for you to try, an example of an Arrhenius, typical Arrhenius type problem. Notice in that two temperature form, there are a lot of variables. That means there's a lot of ways to ask these questions and a lot of different things to solve for. You can solve for the activation energy, you can solve for temperature 1, temperature 2, or K1 or K2. So you can solve for any one of those things. Can't solve for more than one because it's only one equation. So you have to be given everything else. But you want to make sure that you're comfortable with the algebraic manipulation of that equation to be able to solve for any one given variable. So in this example, we have a K value, a rate constant, for a particular temperature, 298, and we want the value of K at a different temperature, 350 K, and we're given the activation energy there in kilojoules per mole. So try to work that one out. I will have the solution for that one posted on YouTube. Best of luck to you on that one. If you have any questions, make sure you contact me.